As you've already been told, the topic we've chosen today is deflection of beams. This covers the civil engineering disciple, and the maths involved will be differential equations and integration. In engineering, deflection is the degree to which a structural element is placed under a load. It may refer to an angle or a distance. The calculation of deflection is an important part of structural analysis and design, and is done so using the mathematics we have learned, including differential equations and integration. Engineers use differential equations and integration to determine the maximum deflection of certain beams under specific loads and also determine failure loads. The beam is a fundamental part of most structures we see today and is used in a variety of ways. Today we're looking into the bending moment and the deflection of a beam and how it relates to real-life engineering applications. Mathematics such as differential equations and integration go hand in hand in the design, construction and completion of civil engineering today. From a design aspect, it is crucial to determine safety loads and limits, which can therefore be used firsthand in the design of a project being completed. These safety loads are of great significance, so determining braking strains such as max deflection, mathematics is of great significance in doing so. Most procedures today for finding beam deflections are based on differential equations of the deflection curve and their associated relationships. The process followed in an engineering example involves determining the bending moment equation. From this, a differential equation is formed which can be integrated to determine the slope and deflection of the beam. So now we should have a basic understanding of the role beams play in engineering and how they work. Now we're looking to how mathematics and engineering play hand in hand. The following question asks us: determine the equations of the deflection curve for a simple beam AB supporting a uniform load of intensity Q acting throughout the span of the beam. So the first step we need to do is make a cut somewhere along the beam to determine our bending moment equation. As you can see from the image on the screen, this is how it is done. We then calculate our bending moment equation, which is also seen as a differential equation. Once we have obtained our bending moment equation, we can now make the substitution of m equals EIV double dash into the equation. So now we have our differential equation, which is seen as EIV double dash equals QLX on 2 minus QX squared on 2. By multiplying both sides by dx, it allows us to integrate both sides, which gives us an equation for the slope. But using the power rule, we can simply integrate both terms on the right hand side and integrate the term on the left hand side. Now we have a constant that must be evaluated. This can be done by when v dash equals 0, x equals L on 2. By substituting x equals L on 2, we can obtain that c equals minus QL cubed on 24. This then can be implemented back in the equation to give the equation for the slope. Finally, we must integrate the equation again to determine the deflection equation. From integrating both sides, you can now see we have obtained the equation EIV equals QLX cubed on 12 minus QX to the power of 4 on 24 minus QL cubed x on 24 plus c. The constant of integration c may be evaluated from the condition that the deflection of the beam at the left-hand support is equal to 0. That is, v equals 0 and x equals 0. We can therefore determine that c equals 0. By rearranging the equation we have obtained, we can determine the final equation for the deflection at any point along the beam. As you can now see, we have calculated an equation for the max deflection of the beam, which can be seen taking place in the middle of the beam. In conclusion, the example above illustrates the process of setting up and solving the differential equation of the deflection curve through the process of integration. As you can see, we have calculated an equation to determine the deflection at any point along this beam and also for the maximum deflection which occurs at the mid-span for this particular mathematical problem.